In this video, we're going to see what is the change in entropy in a Carnot cycle. The purpose of the video is to demonstrate that entropy is a state function. So the change in entropy in a cycle is actually going to be zero. Now, we're choosing a Carnot cycle because it's a beautiful example of a heat engine, but the results are going to be entirely general. So they would apply to any cycle. So let's actually start with the definition of the cycle. What are the steps? Here you have a pressure versus volume diagram for a gas, and the gas is undergoing a cycle A, B, C, D. Now here we have two isotherms, one at a hot temperature and another one at a lower temperature. So the first step here is going to be an isothermal expansion of that ideal gas, and all of the steps will be reversible. Okay, so A to B will be an isothermal reversible expansion. From B to C, the temperature is dropping and the volume is expanding. We're actually going to do this adiabatically, so that will be an adiabatic expansion reversible of an ideal gas. Now C to D, you're traveling along an isotherm, so it will be a reversible compression isothermal of an ideal gas, and then D to A is also going to be adiabatic reversible, so that is going to be an adiabatic compression to get back to the start. Okay, so here we go again, four steps. The first one is a reversible isothermal expansion, then adiabatic expansion, then reversible isothermal compression, and then adiabatic compression. Those are our four steps that complete the cycle. And the point of all this is to try to calculate the change in entropy in that cycle. All right, so we know that the thermodynamic definition of entropy is simply the integral of Qrev over T. Okay, and so if we're able to calculate this value for each one of the four steps of the cycle, we just have to add that up to calculate the total change in entropy in the cycle. All right, so the adiabatic steps are fairly simple because by definition, Q is equal to 0, okay, in an adiabatic step. So in that step and that step, that energy transfer as heat is 0, that means that there's no change in entropy at all. Okay, so the only two steps that we have to worry about are these reversible isothermal steps, A to B, and then C to D. All right, so let's do that. Notice that those steps are isothermal, so integration of this expression is just going to be the reversible heat divided over the temperature for each one of these two steps. For the entire cycle, then, what we have is that is going to be the heat, the reversible in going from A to B, divided over the temperature, which in that particular case is the temperature of the hot isotherm, and then the reversible heat in going from C to D, divided over the temperature of the cold isotherm. Okay, so let's talk about that reversible heat in those isothermal expansions. We know that in isothermal expansion of an ideal gas, there's no change in internal energy because the internal energy of a gas only depends on temperature. And if the temperature doesn't change, then the internal energy doesn't change. Okay, so we have that, well, because delta U is equal to 0, then what's going to happen is that for each one of those steps, you will have that the reversible heat is going to be equal to the minus reversible work. And we know from our earlier work that reversible work is going to be minus nRT natural log of the final volume V2 over the initial volume V1. Okay, so there is going to be the reversible heat in each one of those two steps. All right, so let's then actually plug that out into the expression here. Okay, we have then that delta S is going to be the reversible heat, so number of moles R, then T hot for A to B, and then the natural log of the final volume or over the initial volume, so there is going to be the volume of the point B and the volume of the gas at point A. And then we have the same expression or a related expression for the isothermal reversible compression going from C to D. So that is going to be N, R, T, in this case this is cold, okay, and then the natural log of the final volume, VD, over the initial volume, VC. Of course, these reversible heats are divided by the temperatures, so let's not forget that. That is divided over T hot, and this is all divided over T cold. And we're ready to see that there's some cancellation here. Of course, those temperatures cancel each other out, so that cancels with that. And then this cancels with this. Okay, so that is the expression that we have to try to figure out. Now, the only unknowns here is whether these volumes are actually related to each other or not. And they are. And the way that we're going to see this is by looking at the adiabatic steps, because we actually know what the relationship between volumes and temperatures are for any adiabatic step, right? So if we now recall our work with adiabatic expansions that we had on our unit on the first law, what we'll remember is that the relationship between pressures and volumes in an adiabatic expansion was volume initial multiplied by the initial temperature to a factor C is equal to the final volume multiplied by the final temperature to a factor C. And this power C is just the ratio of the heat capacity constant volume per mole divided over R. Okay? All right, so what we're going to do is then use this relationship between initial volumes and temperatures and final volumes and temperatures for both of the adiabatic steps, B to C, and then D to A. All right, so for the first one, B to C, the initial volume is V sub D, the initial temperature is T hot, and then the final volume will be V sub C, and the final temperature will be T cold. Okay, so that is for the BC step. Let's do the same thing for the D to A step. Okay, the initial volume will be VD, and then the temperature will be T cold to the power of C, and then the final volume will be VA, and the final temperature will be T hot to the power of C. Okay, now what we actually do is consolidate this by multiplying the top expression by the bottom expression. All right, so that is going to result in V sub B multiplied by V sub D, and then T hot to the C over T cold to the C, and this is equal to VCDA multiplied by the products of the temperatures, which I'm just going to write out here. Okay, that will be just T cold to the C, and then T hot to the C. Okay, so notice that those temperatures all cancel. All right, so that cancels with that one, and then we get to a very simple, very beautiful relationship between volumes, right? So we can write that V sub D over V sub C is equal to V sub A over V sub B. Okay, and that's something that we can use very nicely in that expression. Okay, notice that one of the things that we can do here in that expression is to say, well, I can revert the order of this ratio, right, in turning to V sub A over V sub B, and that will just change the sign of the logarithm, so there's going to be a negative sign right there. Okay, and then from this relationship between volumes, we see that the ratio of V of A to B of B is the same thing as V sub D and V sub over V sub C. So there you go, V sub D over V sub C. All right, so what we actually see is that, of course, these two terms are exactly the same, right? The entropy that you gain here is exactly the same thing as the entropy that you lose there. So overall, the change in entropy in this cycle is equal to 0. Okay, so that is a demonstration for how entropy is a state function. To calculate changes, you actually, the pathway really doesn't matter. The only thing that matters is what the initial step is and what the final step is. And then in a cycle, the initial step and the final point is exactly the same, so the change in entropy will be 0, and we've been able to demonstrate that with this Carnot cycle. In the next video, we're going to continue to talk a little bit about this Carnot heat engine by talking about a little bit about the efficiency of this engine in thermodynamic terms.